Hello everyone, I am Jesmin and I'm going to talk about how to accelerate Quicksilver, a proxy app for the Mercury software package that simulates the Monte Carlo particle transportation problem to achieve 1.8x speed up on the state-of-the-art multicores compared to its original implementation. Quicksilver tracks particles as it transports through a polyhedral domain of material decomposed into domains, meshes, cells, and facets. Quicksilver replicates the control divergence, memory access, and communication patterns of Mercury. As a result, the lessons learned in optimizing Quicksilver have direct implications for Mercury. Quicksilver is being actively used in novel architectures co-design efforts, and its performance on any hardware influences the procurement decision at DOE. It's challenging to parallelize Quicksilver efficiently because it contains complex and irregular kernels with many execution paths. Control flow is dominated by branching. Performance is dominated by latency-bound table lookups. It uses an array of structure-style programming that requires multiple levels of indirections, and it accesses multi-gigabytes of data either randomly or using non-unit strides, which are also difficult to cache efficiently. Quicksilver has very low vectorization opportunities, and state-of-the-art GPUs provide little performance advantage. The original Quicksilver paper shows that NVIDIA Pascal 100 GPU performs only 35% better than Power 8 CPUs. Now let's see how Quicksilver works. Quicksilver tracks each particle from its beginning to its end using a history-based particle tracking approach. Each time step can be divided into three phases: cycle init, cycle tracking, and cycle finalize. Cycle tracking is the key kernel where for each particle in parallel, it calls the segment outcome function to find the most likely event that the particle is going to go through, and then it executes that selected event and repeats the process. And that event could be either going through a collision or crossing a facet or reaching census. When we profiled this code using Intel Advisor, we found that the two major time-consuming functions, which are taking almost 96% of the total runtime, is basically collision event and the segment outcome functions. Collision event is the function that gets executed when a particle experiences a collision, and that was our main optimization target. So when we profiled the collision event function, we found that 70% of its time was spent in three nested multi-exit loops that is used to find isotope and reaction IDs for the collision by doing a linear search in the nuclear database. In this section, the most heavily used data is accessed using 6 levels of indirections. We optimized this section by replacing a linear search with a binary search, which reduces the search time from order n to order log n, where n is number of isotopes times number of reactions. For this, we copied the content of the nuclear data into a contiguous table in a preprocessing step. Then we stored a prefix sum of the collision probabilities into another contiguous table. This allowed us to do a binary search over the new prefix summed table to find isotope and reaction IDs. This improved the performance by reducing the computational cost from linear to logarithmic, and the newly created data structures are also more performant than the original one because they are more compact, and it improves caching efficiency. We also did some minor code optimizations such as function inlining, scalar replacement, dead code elimination, which improved performance by 5 to 7%. Then we tested this code on state-of-the-art Intel Xeon Cascade Lake Platinum processor with 164,000 particle, and we achieved 1.8x speed up compared to the original implementation. This improvement strongly scaled till 16 cores, after which the performance dropped. The good news is Quicksilver is a throughput scaling problem. It uses MPI to weak scale across ranks and OpenMP to strong scale inside an MPI rank. Improvement inside a single MPI rank, which may occupy A single socket or even a sub-socket should be faithfully replicated across ranks during throughput scaling, and thus the algorithmic improvement that we have shown in this poster should be valuable at scale if the number of cores remain below 16. We use Quicksilver for software and hardware co-designing, and we would like to explore other optimization opportunities in any hardware platform of interest. Thank you for listening, and if you have any further question, please feel free to email me at jasminjahantithi@intel.com. Thank you.